talk about fuel and fuel systems in aircraft. And to begin with, let's discuss some general characteristics and properties of aviation fuels. First of all, the anti-knock characteristics. You don't want the fuel to be detonating in the engine, and so the detonation or anti-knock characteristics of a fuel can be improved by adding a knock inhibitor, which basically is tetraethyl lead. Adding lead to the gasoline will improve the anti-knock characteristics. Now, the measure of a gasoline's tendency to vapor lock is obtained by using the Reid vapor pressure test. The Reid vapor pressure test measures a gas's tendency to vapor lock. If aviation gasoline vaporizes too easily, too readily, what will happen is the fuel lines will be filled with vapor, and that decreases fuel flow. It does not increase fuel flow, it decreases fuel flow because you've got vapor in the fuel lines. The maximum vapor pressure allowable for aircraft fuel is 7 psi, and the allowable vapor pressure of aviation gasoline is lower than the vapor pressure of automotive gasoline. You have to be more careful about the vaporization characteristics of aviation gasoline because of the fact that it goes up to high altitudes, so the allowable vapor pressure is lower than for automobiles. Now, some aviation fuels are aromatic fuels, particularly the high-octane fuels, but a disadvantage of using aromatic aviation fuel is that it does deteriorate rubber parts. So you have to keep a much closer watch on those kinds of parts in the aircraft. It will deteriorate rubber, and in a lot of cases, synthetic rubber parts will have to be used. Now, one of the things about fuel is that temperature affects the weight of the fuel. Temperature affects the weight of the fuel, and cold fuel is heavier per gallon than warm fuel is going to be. And the aircraft engine is really getting its energy by the weight of the fuel, so you're going to, when you have cold fuel, you're actually going to have more energy available for the aircraft engine as far as the volume is concerned. Now, as far as jet fuels are concerned, jet fuels are more susceptible to water contamination than aviation gasoline is. And the reason for that is because jet fuel, turbine fuel, is more viscous than gasoline is. It's thicker, it's more viscous than gasoline is, and therefore what happens is it tends to hold that water in suspension. Using turbine fuels in aircraft has resulted in having problems that you don't associate with aviation gasolines. And one of the problems that comes along with turbine fuels as opposed to aviation gasolines is microbial contaminants. Microbial contaminants, basically organic material growing in the turbine fuel. It's produced by various forms of microorganisms. They live and they actually multiply in the water that is suspended in the jet fuel, what the FAA calls water interfaces of the jet fuels. They're multiplying in that water. Now, if you've got microbial growth in a jet fuel tank and it's not corrected, what's going to happen is all those microbes, all that growth will actually interfere with the fuel flow and the fuel quantity indicators. You're going to get interference with fuel flow and fuel quantity indicators, and also that growth can cause electrolytic corrosive action in the metal tanks. Corrosive action in the metal tanks if you don't stop that growth. So how do you stop the microbial growth problem in jet fuel? Well, what you do is you use anti-icing and antibacterial additives like Prist. One of the things you've got to do is get the water out of the fuel, and the other is actually kill off the growth, and additives like Prist will do both of those tasks for you. Now let's talk about fuel system design. If you've got large aircraft like a 727, very typically you're going to have all kinds of lines running around between the tanks, between the engines, multiple manifolds in there. And the whole purpose of that fuel manifold system is to basically let you move fuel wherever you want to do it. What the fuel manifold system allows you to do is, first of all the tanks can be serviced through a single connection. You can do pressure fueling with all the tanks serviced through a single connection. In addition to that, any engine can be fed from any tank in the airplane, and that gives you redundancy, a lot of value to that in case you've got a problem with any one tank. All engines can be fed from all the tanks simultaneously. It just depends on how you set up the valves in the system. Gives you lots and lots of options. And in addition to that, a damaged tank can be isolated from the rest of the fuel system. If for some reason you get a leak in the tank or a lightning strike or any kind of damage, you can isolate it from the rest of the fuel system, and that's what a fuel manifold system allows you to do. Now, when it comes to fueling an airplane, in an effort to avoid people putting the wrong fuel into airplanes and thereby causing accidents, there are some minimum required markings that have to be placed on or near the fuel filler cover. For reciprocating engine-powered airplanes, those are the word avgas, so that you don't accidentally put jet fuel in it, and also the minimum fuel grade required. For instance, 100 octane or 100 low lead. If it was a jet airplane instead, a turbine-powered airplane, instead of avgas, obviously it would say jet fuel. And the whole idea behind these required markings is that they want to make sure the airplane does not get misfueled. Now let's assume that you're routing a fuel line like this one here between two rigidly mounted fittings. The way you want to do that is to have at least one bend between the fittings, and the idea behind that is strain relief that will help prevent the line from cracking. You do not have to use flexible hose, but what you do want to make sure of is that you've got at least one bend in it to help relieve the strain. Now, fuel system components must be bonded and grounded, and the idea of that is to drain off static charges to prevent sparks and thereby prevent fires and possibly explosions. The main fuel strainer will be located down at the lowest point in the fuel system. Usually it's going to be on the bottom of the cowling, one side or another in the engine compartment area. And the purpose of it is to trap any small amount of water that may be present in the fuel system. And that is the main strainer down at the lowest point in the fuel system. A lot of times with a lot of aircraft, you've got a gravity feed fuel system that can supply fuel to the engine from more than one tank at a time, like this 172. And in that case, the air spaces between the tanks have to be interconnected in order to vent those tanks properly. Let's talk about those fuel tank vents. One purpose of the fuel tank vent is to limit the pressure differential between the tank and the atmospheric pressure. What the vents are trying to do is to maintain atmospheric pressure within the tank, and the whole purpose of that is so that the fuel will flow down to the engine properly in that feed system. Now, on the bottom of the tanks, you're going to have a fuel tank sump. And the primary purpose of that fuel tank sump is to give a place where the water and dirt accumulations, whatever's accumulated in the tank, can be collected and drained out, and give you a chance to check it and see if you're getting any contamination in the tank. There's a number of different ways that fuel tanks can be placed in an aircraft. One way is what is called an integral fuel tank. A Citation, for instance, and a lot of other planes have an integral fuel tank, and a more common name for it is a wet wing. The integral fuel tanks, or the wet wing, are formed by the aircraft structure itself. There's no other tank, there's no other bladder or anything. It's simply formed by the aircraft structure. And the reason that integral fuel tanks are used in a lot of aircraft, particularly in larger aircraft, is to reduce the weight. It gives you a lot less weight if you can use the structure of the wing itself in order to create the fuel tank. Now, in the fuel tanks, you're going to have flapper valves that are used as check valves in order to keep the fuel from going back away from where you want it to be, for instance, around the boost pumps. Flapper type check valves, for instance, are used in integral fuel tanks, and what they're used for is to prevent the fuel from flowing away from the boost pumps. So as the fuel accumulates around the boost pumps, those flapper type check valves keep the fuel there, prevent it from flowing away. Now, fuel tanks will also have baffle plates in them, and the purpose of a baffle plate in a fuel tank is to resist the fuel surging back and forth within the tank. It slows the fuel down and keeps it from sloshing and surging around. Some aircraft, for instance the Cessna 182, have got bladder type fuel tanks. The bladder type fuel tank is just what its name says, a bladder that goes inside the aircraft wing, and that's what holds the fuel. Now, if that's going to be left empty for an extended period of time, for instance, the airplane is going to be not flown for a long period of time, then the inside of that tank needs to be coated with a film of engine oil, and the reason for that is to make sure that the bladder tank does not deteriorate. Coat the inside of it with a film of engine oil. If you have a multi-engine aircraft, what you're going to have is a fuel cross-feed system. So take a look in the FAA's Appendix 2 at Figure 17. And it shows the fuel cross-feed system on a twin-engine aircraft. The primary purpose of a cross-feed system is to allow you to feed any engine from any tank. You can feed any engine from any tank. That gives you a lot of flexibility. Now, there are various valves in this cross-feed system, and they're going to ask you what the purpose is of the pump cross-feed valve. There is a tank cross-feed valve, and then down in the center of Figure 17 there is a pump cross-feed valve, and the purpose of the pump cross-feed valve is to allow the operation of both of the engines from one tank. It is not to allow you, this cross-feed valve is not to allow you to pump fuel from one tank to another. That's what the tank cross-feed valve does, but the pump cross-feed valve allows you to operate both the engines from one of the tank. Now, the cross-feed systems are used in multi-engine aircraft primarily to maintain a balanced fuel condition. If you've got more fuel in one tank than another, you can feed both of the engines out of one tank, balance the load, and then go back to feeding each engine off of its normal tank. Let's talk about fixing fuel tanks. Sometimes you need to repair a fuel tank. Now, if you're going to have to repair a fuel tank, you need to empty the fuel out of it first. And you want to avoid conducting any defueling and tank purging operations in any enclosed space. Do not do it in an air-conditioned building or any enclosed space. You want to be out in the open air in a well-ventilated area. Now, an integral fuel tank, one that's basically the wet wing, you should purge with carbon dioxide, with CO2, before you try and do any repairs on it. You want to make sure that the fuel vapors are out of the tank before you start doing any repairs. When you're repairing integral fuel tanks, riveting can be used usually to repair those tanks because they are part of the basic aircraft structure, so you can use riveting as you would on the aircraft structure to repair those integral fuel tanks. Now, some aircraft, such as an older 172, actually have metal tanks in the wings for their fuel tanks. Not rubber bladders and not wet wings, but actual metal tanks in the wings. If those need work on them, for instance, welding, what you want to do is take the tank out, but before you do any welding, make sure that you steam clean it very thoroughly. That way you'll get rid of any fuel or fuel vapors that might cause you a fire or explosion problem. Now, when you're done, if you want to inspect that removable rigid fuel tank for leaks, the best way to do it is to pressurize the tank with air and then brush it with soapy water and look for bubbles. If you see bubbles, it means that the air is coming through into that soapy water and you've got some leaks. It's not practical to submerge the tank in water or to fill it with water in order to look for any streams or dribbles coming out. The easiest way is to simply pressurize it with air and then look at that soapy water to see if you have any bubbles indicating leaks. Now let's talk about fuel pumps. First of all, boost pumps. The fuel boost pumps in an aircraft are operated to provide a positive flow of fuel to the engine. They prevent bubbles in the fuel after it leaves the tank if atmospheric pressure is lower than the fuel vapor pressure. And so that fuel pump basically helps make sure that the engine keeps running. Now, some boost pumps are a centrifugal type boost pump that is buried or sunk in the fuel tank itself. The centrifugal type boost pumps are used in fuel systems, particularly of aircraft operating at high altitude. They supply fuel under pressure to the engine-driven pumps, and they prevent the vapor lock. Now, the centrifugal type pump, you should know, separates air and vapor from the fuel. Here's air and vapor coming out of that pump before it enters the line to the carburetor. How much fuel pressure you've got on the outlet side of a centrifugal type fuel pump basically is regulated by the pump's design and its own internal clearances. It is not regulated by the speed of the engine, because when you're working with a submerged single-speed centrifugal type fuel pump like this is, it's regulated by the pump's design and its own internal clearances. That's what controls the outlet fuel pressure. A centrifugal type pump like this is not a positive displacement pump. The primary fuel pump on the engine does tend to be a positive displacement fuel pump, and a positive displacement fuel pump has to have a fuel pressure relief valve. It's required by the FAA regulations on a positive displacement fuel pump because it's always putting out the same amount of fuel through the pump, and the engine is not always able or ready to accept that much fuel pressure, and so you have to have a fuel pressure relief valve on a positive displacement fuel pump. Okay, so the FAA will say to you on the test, does a centrifugal fuel pump have to have a fuel pressure relief valve? Well, is a centrifugal fuel pump a positive displacement pump? No, it's not, and therefore it does not have to have a fuel pressure relief valve. On the other hand, they'll give you another question that says, do you need a fuel pressure relief valve on a sliding vane type fuel booster pump? A sliding vane pump is a positive displacement pump, and if it's a positive displacement pump, does it have to have a pressure relief valve? Yes, it does. So a pressure relief valve is required in a sliding vane fuel booster pump. Now, a vane type pump like this will also have a diaphragm in it, and the purpose of the diaphragm is to compensate fuel pressures for altitude changes, so that as the aircraft changes altitude, you get changes in the fuel pressures. Let's talk now about our fuel quantity indicators. Figure out how much fuel there is in the aircraft. There's 4 basic types of fuel quantity gauges. There's electronic types. We're going to talk about all of these. There are electrical gauges, there are mechanical gauges, and there are sight glasses. Sight glass is pretty obvious. There's just a glass coming up. The old Yankees had it and a lot of other aircraft where you can actually see how much fuel there is up through the sight glass. Mechanical ones, you see that for instance in the old Pacers where you've got basically a cork and a little metal wire sticking up out of it, and depending on how much fuel you've got in the tank, the cork and the wire bob up and down. Electronic and electrical we're going to talk about in more detail in just a minute. Now, as far as the calibration on these fuel quantity gauges are concerned, they have to be calibrated to read 0 in level flight if the quantity of fuel remaining in the tanks is equal to the unusable fuel supply. In other words, when you've used up all your usable fuel, in that case, the gauges should read 0. You don't want the gauges reading 5 gallons if the 5 gallons is not usable to the aircraft. So when you get down to the unusable fuel supply, those gauges should read 0. They should be calibrated that way in level flight. Let's talk now about the electronic type or capacitance type fuel quantity indicating system. There's 4 basic elements on that capacitance type fuel quantity system. You've got a bridge circuit, you've got a signal amplifier, you've got an indicator in the cockpit, and you've got a transmitter unit, you've got a tank unit that is sending the signal. Let's take a look at this unit and see what we've got there. In the tank, there are no moving parts as far as a capacitance type or electronic fuel quantity system is concerned. What you've got is a probe, or maybe several probes, that are installed in the fuel tank. This is the probe here, and here are the electrical wires that are coming out of it. We have fuel in most of the tank, but then we have air up above it. The probe or the tank transmitter basically is an electric capacitor. It's got fuel and air located above the fuel, which act as a dielectric. Now, a dielectric means a non-conducting material. So basically what you've got is you have charges trying to move from one side of the electric condenser, which is the probe, to the other. But you have the fuel and you have the air, which are the dielectric, the non-conducting material, between the 2 parts of the probe or the condenser. What happens is that the non-conductivity of the fuel and the air is different. So how much electricity can move from one side to the other depends on what the ratio is between the fuel and the air in that tank. The capacitance type gauges tend to be very accurate because of the fact that they do not have any moving parts in them. And also, they're very accurate in measuring fuel level because they measure by weight. They measure by pounds rather than in measuring by gallons. And when it measures by pounds like that, instead of measuring in gallons, the measurement will be more accurate because of the fact that the volume of the fuel varies with the temperature change. So fuel quantity measured in pounds instead of gallons is more accurate. You've always got the same number of pounds, but the gallons of fuel will change depending on what the temperature of the fuel is. Now, another type of fuel quantity system is the electrical type fuel quantity system, and what that's got is an indicator in the cockpit, and there is a float-operated transmitter in the tank. And the purpose of that float-operated transmitter is to send an electric signal to the fuel quantity indicator. It is not a mechanical connection. It's an electrical signal going from the transmitter in the tank, which is activated by the float, and then sending the electrical signal to the indicator in the cockpit. Some aircraft have a fuel totalizer in the aircraft. 727 is one of those, and the fuel totalizer indicates the amount of fuel in all of the different fuel tanks. In this case, 3 different tanks, and the fuel totalizer tells you how much you've got in all the tanks together. And that is one very definite advantage of the electrical or the electronic fuel quantity indicating systems. Several fuel tank levels can be read on one indicator, and the indicator can be located any distance from the tank. You don't have to worry about a mechanical or visual connection, so you can put the indicator any distance from the tank that you want to. Now, on large transport category aircraft, another way to measure the amount of fuel in the tank is to use a drip gauge. And a drip gauge, unlike what its name sounds, is not something you use to check if something's leaking, like fuel or oil. You can use it. It's basically a visual way of measuring the amount of fuel in the tank using a gauge in the wing and basically filling it with fuel and seeing exactly when it starts dripping out the end. Drip gauge measuring the amount of fuel in the tank. Now, how do you tell how much fuel you're using? Well, one way is with fuel flow indicators. And fuel flow transmitters in the fuel lines are designed to transmit data electrically, so you get an indication of how much fuel flow is actually going through the engines. Some aircraft, instead of having fuel flow indicators, have fuel pressure indicators. A fuel pressure gauge, like you have in, say, an Archer, is a differential pressure indicator. It's a differential pressure indicator because it's using fuel pressure and ambient atmosphere in order to get a differential pressure indication. And the fuel pressure gauge indicates the pressure of the fuel as it's entering the carburetor, the pressure of the fuel as it's going into the carburetor. Now, large aircraft, particularly multi-engine aircraft, will very often have a fuel pressure warning system. And that's what we've got with these amber lights on the 727. When they illuminate, you've got low fuel pressure. A fuel pressure warning signal system prevents you from allowing the fuel supply in one tank to run out, to become exhausted, before you switch the selector valve to another tank, because when the pressure gets low, that light illuminates and tells you that you're running out of fuel. The fuel pressure warning, therefore, gives you the first positive indication that you need a changeover from one fuel tank to another. First really positive indication because it tells you you're losing fuel pressure because you don't have enough fuel in the lines coming in. What it uses is a pressure-sensitive mechanism, a pressure-sensitive mechanism that actuates the fuel pressure warning system. And that pressure-sensitive mechanism can be adjusted to change where the fuel pressure warning lights come on. You can change the fuel pressure warning limits by adjusting the pressure-sensitive mechanism. The transmitter in the fuel pressure warning system basically takes fluid pressure in the lines, however much fuel pressure there is in the line, and converts that to an electrical signal. And when the fuel pressure drops below the limits that you've set the mechanism for, the fuel pressure warning switch contacts close and the warning light comes on. Now, if you're dealing with a reciprocating engine aircraft as opposed to a turbine engine aircraft like we have here, in that case, the fuel pressure line of the carburetor is where the pressure is taken for the fuel pressure warning signal. Now, if you're going to troubleshoot a system like this, you need to use the manufacturer's maintenance manuals because they're all going to be different, and you need to look at the maintenance manuals if you're going to do any effective troubleshooting on it. Fuel system icing is another problem that gas turbine engines have, and the fuel systems in turbine engines are very susceptible to forming ice in the fuel filters. And you want to prevent the ice from forming in the fuel filters, and a very common way of doing that is to add anti-icing fuel additives. You can heat the fuel, which we'll talk about in a minute, but another way to do it to take care of the problem is to add anti-icing fuel additives. Now, on some aircraft, what they do is heat the fuel. For instance, on the 727, you've got a fuel temperature indicator. The fuel temperature indicator, and you've got a gauge right down here or below the fuel heat panel, the fuel temperature indicator tells you when the fuel may be in danger of forming ice crystals because it tells you what the temperature of the fuel in the tanks actually is. Okay, that's nice. You know the temperature of the fuel in the tanks. What do you do about it? Well, you've got a fuel heat system. And what the fuel heater does is it protects the fuel system from ice formation because it operates as a heat exchanger. It takes hot bleed air off the engine and runs it in a heat exchanger past the fuel, which warms up the fuel and prevents the ice from forming. The aircraft fuel heater can be used, by the way, to thaw ice in the fuel screen. If you actually have already gotten ice in the fuel screen, you can use that fuel heater to actually go ahead and thaw the ice. Now, one way to heat the fuel is to use this engine bleed air. But another way to do it is to use the engine lubricating oil as a source of heat. Some aircraft have one or the other, some aircraft have both. So either engine bleed air or engine lubricating oil can be used as a source of heat for the fuel in order to keep ice crystals from forming in the fuel. Some aircraft require that you have a good way to get rid of the fuel to dump it. On this 727, the dump chute is out here on the right wingtip. There's another one over on the left wingtip, and that's how you jettison fuel, get rid of the fuel if you need to. You might need to get rid of it if you've just taken off and have an emergency and have to go back and land, and you have to get down below your landing weight. Both transport category aircraft, like this airliner, and general aviation aircraft require a fuel jettison system under certain conditions if the maximum takeoff weight exceeds the maximum landing weight. Now, interestingly enough, what you really have to remember about this question is the regulation numbers for the regulations that cover the requirements for fuel jettisoning. Those are FAR 23, FAR Part 25, and CAM 4B. FAR 23 covers the airworthiness requirements for most aircraft. FAR 25 covers them for transport category aircraft, and CAM stands for Civil Aeronautics Manual, and that goes back to before the FAA was the FAA. Now, when you're dumping fuel, you don't want to accidentally dump all of your fuel. So dumping past the limits that the regulations prescribe is prevented by having dump limit valves or by having a low fuel level circuit. And the dump limit valves or the low level circuit will shut off the fuel dumping, will stop the fuel jettisoning when the fuel gets down to whatever the limits are that the regulations prescribed for that particular kind of aircraft. Now, the way the fuel is usually jettisoned, the dumping is usually accomplished, is through a common manifold and outlet in each wing. So the tanks will all be connected together into a common manifold, and then it will dump out through an outlet, but you'll have one in each wing. The way you maintain lateral stability while you're dumping fuel is by having two separate independent systems on each side of the aircraft so that you don't get one wing of the aircraft heavier than another. And the way you make that fuel move overboard is by boost pumps. In other words, you're turning on boost pumps that actually pump the fuel overboard. You don't want to depend on it to just flow out on its own. You want to make sure in a fuel jettison system that the whole system and the operation of the system are not going to be a fire hazard, that they're free of fire hazards. And one of the requirements, as far as that's concerned, is that the fuel has to discharge clear of any part of the airplane. So you're not going to discharge it up in the middle of the belly because it's then going to be spraying back over the aircraft. A wingtip here or the very back of the airplane, someplace where it's clear of any part of the aircraft would be okay. And the fuel jettison valve is designed so that flight personnel, the flight crew, can close the valve at any time during any part of the jettisoning operation. You want to make sure that it stays under the control, the operation stays under the control of the flight crew, so they can stop dumping fuel, stop jettisoning it anytime they want to. Okay, we've gotten rid of fuel in the air, but how about when we're fueling aircraft on the ground? Transport category aircraft typically have a pressure fueling system. The pressure fueling system allows the aircraft to be fueled from one point under fairly high pressure, makes it a lot quicker and a lot easier. But they vary with the different aircraft manufacturers. And so the fueling operator, whoever's doing the fueling, must consult the aircraft manufacturer's instructions for the detailed procedures to be followed. You cannot assume that because you know how to do it on one airplane, you automatically know how to do it on all aircraft. Pressure fueling is a lot more practical than the over-the-wing fueling that's used for most general aviation aircraft. It's much more practical for large aircraft than the over-the-wing fueling because it saves a lot of time. There's a single point on the aircraft that you have to hook up to, and you can fuel the entire aircraft from there. Now, for small aircraft, general aviation aircraft, pressure fueling is much less of an advantage, and the reason that it's less of an advantage for small aircraft is the limited fuel tank area. A 727 has got a lot of fuel tank. You got to put a lot of fuel in, and it really makes it handy to be able to hook up to one connection and pump it in under high pressure. Small aircraft, it doesn't make that much difference because you don't have that much fuel tank space or area. You don't have that much volume of fuel that's going on. Now, one of the flight-related advantages for safety that a pressure fueling system has got is that it reduces the chances for fuel contamination. Because of the fact that you have a tight fit to the wing and you're pumping the fuel in under pressure, you have a lot less chance for fuel contamination from dust or water or whatever might be running around in the air. That is a flight safety related advantage. There are other advantages, but that's the one they want you to remember applies as far as flight is concerned. Now, how do you do pressure refueling? In the 727, the refueling station is out here on the right wing. This is the panel that comes down to show you the valves and lines and instructions that are inside. And inside there, you've got your hose connections, you've got indicators and various valves you can turn. You'll have a panel that tells you what the instructions are. So for a pressure fueling system, you've got a pressure fueling hose and a panel of controls and gauges that allow one person to either fuel or defuel all of the fuel tanks or any single fuel tank on the aircraft. And the instructional procedures are normally placarded on the fuel control panel access door, so you know exactly what you're supposed to do. Now, before you start pressure fueling an aircraft, one of the things you have to do is make sure that the pump pressure on the fuel truck is correct for that refueling system. They are different. You have to check and see what you need and then make sure that the pump pressure on the fuel truck matches the fueling system for that particular aircraft. During fueling operations, you want to make sure that the fuel you're supposed to use is appropriately identified. You want to use the right fuel for the right type of aircraft. Now, even if you fuel an aircraft from a truck or a storage tank that you know is not contaminated with dirt or water because you've been checking the tank or the truck, you still have to do periodic checks of the aircraft's fuel tank sumps and system strainers. It still could have contamination because you can get contamination from other sources. Water just from condensation. You can get particles in the fuel from the system itself. The fact that the tank or the truck is free from dirt or water does not automatically mean that you're never going to have any of that in the tanks. You still need to drain the sumps and the tank strainers. Now let's assume that you fueled a jet and now you're going to need to defuel it. Defueling should be accomplished in the open air for good ventilation. You don't want to do it inside an enclosed building. Now, if you're defueling an aircraft with swept back wings, it is important to defuel the outboard wing tanks first. And the reason for that is, with the swept wings, if you defuel the inboard tanks first, the weight of the fuel would be out here in the wingtips, which is behind the center of gravity, and the chances are the plane could tip back on its tail. So defuel the outboard wing tanks first. Now, if you're defueling an aircraft, even one that has a gravity fueling system as opposed to a pressure fueling system, you still need to consult the aircraft manufacturer's instructions if you want to make sure that you defuel it properly and get all of the fuel out of the aircraft. Now let's talk about some troubleshooting on the fuel system. First of all, when you move the mixture control on a normally operating engine into the idle cutoff position, the engine RPM should slightly increase before the engine starts to die. If it doesn't, then the engine's not functioning quite right. Now let's assume that you've got a fuel-injected engine that is running rough. One of the first things you want to check in that case is for excessive fuel pressure. If you've got a fuel-injected engine that's running rough, check for excessive fuel pressure, and that will tell, you can check very easily by looking at the fuel pressure gauge, and that will give you an idea of what's wrong with the engine. If you've got fuel stains around the fuel nozzle, fuel stains around a fuel nozzle indicate that you have a clogged fuel nozzle. Let's talk for a minute about fuel leaks. Now, fuel leaks are usually classified as either a stain, a seep, a heavy seep, or a running leak. A running leak is the only one where fuel is actually dripping off of the aircraft. And the running leak is the only one that's going to automatically ground the aircraft. If fuel is actually dripping off of the aircraft, then it needs to be grounded and have that fuel leak fixed. As far as stains, seeps, or heavy seeps are concerned, whether or not they ground the aircraft depends on exactly where they're located, whether they're in a vented or unvented area, and depends also on exactly how heavy that fuel leak is. As a general rule, stains, seeps, and heavy seeps, in addition to running leaks, the ones where it's actually dripping, are considered to be flight hazards if they're located in unvented areas of the aircraft. What you do not want to have happen is for fuel vapors to build up in an unvented area of the aircraft. So even if the leak is only a stain or a seep or a heavy seep, that much, if it's in an unvented area, that is considered generally to be a flight hazard. Now, if you're trying to troubleshoot a fuel leak in a large aircraft fuel system, a schematic of that fuel system would be very important to use. The larger the aircraft is, the more important it is to have the schematic available to you if you're trying to find a fuel leak. Now, observing the fuel pressure gauge and operating the selector valves will help you to find or locate leaks and defects in the internal portions of the fuel system. When you're inspecting a fuel system, by the way, all the valves located downstream of the boost pumps should be inspected with the boost pumps operating to see if those valves are going to be leaking fuel with the boost pumps pushing fuel towards them. Now, if you want to check for internal leakage of a fuel valve without removing the valve from the aircraft, what you can do is place the valve in the off position, drain the strainer bowl, turn the boost pump on, and watch to see if fuel flows into the strainer bowl, because if the valve is in the off position, fuel should not be able to move through there even with the boost pump pushing on it. Now, when you're installing a fuel line, if you're installing a rigid fuel line of a 1/2 inch in diameter, they want you to know that line needs to be supported at 16-inch intervals. So 1/2 inch fuel line needs to be supported at 16-inch intervals. And that covers what you need to know about the fuel and fuel systems for the airframe course.